In every great story in physics, there are fundamental rules. But in thermodynamics, probably the most important character of all is one we almost never talk about, and that is the wall. Today, we're going to see how two specific types of walls, diathermal and adiabatic, are pretty much the secret gatekeepers that control how all energy flows in the universe. I know it sounds almost too simple to be true, but it is. Every single law of thermodynamics, every engine we build, even how stars work, it all comes down to answering one question. What kind of boundary are we putting around the thing we're studying? So let's dive into that.
You see, in thermodynamics, the very first thing we do is draw a line. That line, that boundary, is what separates our system, the thing we're interested in, from everything else, which we just called the surroundings. But here's the key. That line isn't just a line. It's a gatekeeper. And its personality, well, it determines if energy gets to shout across the border, whisper secrets, or stay in complete and total silence. To really get this, we need to meet the two main players in this game. And don't just think of them as boring, passive barriers. Think of them as characters, each with a very distinct personality that dictates exactly how energy is allowed to act. On one side, we have the dithermal wall. This one is the ultimate socializer. It thinks heat energy should be shared freely with everyone. And on the other side, we have the adiabatic wall. It's the perfect hermit. It absolutely forbids any heat from crossing its boundary, period. And you see diathermal walls all over the place. That cold can of soda sitting on your desk? The aluminum is a classic diathermal wall. It's basically inviting all the heat from the room to come on in and start a conversation. And that thermal conversation, it won't stop until the can and the room are at the exact same temperature. The adiabatic wall, though, that's the dream of perfect isolation. A really good thermos is probably the closest thing we have to it in our daily lives. Its entire job is to do the exact opposite of that soda can, to completely shut down the thermal conversation and keep the heat from your coffee from escaping into the cold room. Now, of course, in the real world, no wall is perfectly one way or the other, but that's the beauty of physics. By creating these perfect, idealized models, the totally social wall and the perfectly isolated one, we can figure out the fundamental rules of how energy actually behaves. So now that we've met our two characters, we can start to see how they don't just influence the game of energy exchange. They literally write the rules. And those rules have some pretty surprising consequences. Now, this might sound like a ridiculously basic question, but the answer is actually really profound. It turns out that our ability to even define what temperature is hinges entirely on one of these walls. Just think about it for a second. If you built a thermometer with a perfectly insulating adiabatic wall, what would happen? Nothing. It would be completely useless. It'd be totally blind to the world around it because no heat could flow in to give it a reading. For a thermometer to work, its wall has to be diathermal. And that's an incredible insight. The very concept of temperature is defined by the permission for heat to be exchanged. That right there is the heart of the zeroth law of thermodynamics. So, when a diathermal wall connects a hot system and a cold system, energy just spontaneously flows from the hot side to the cold side. You've felt this a million times. This keeps happening until everything balances out and both systems hit the same final temperature. We call that stable state thermal equilibrium. Okay, but that brings up a really fascinating question. What happens if we swap in our other character, the adiabatic wall? If a system is perfectly insulated and no heat can get in or out, how in the world can its energy ever change? Well, the answer is a concept that's hugely important in all of engineering: work. And this is where things get really, really cool. If you take a perfectly insulated cylinder of gas and you do work on it, let's say by pushing a piston in and compressing it, all that energy you just put in has nowhere to go as heat, so it gets trapped. It increases the internal energy of the gas and the temperature skyrockets. That is literally why a bicycle pump gets hot when you use it. And the reverse is also true. If you let the gas expand and do work on the outside world, it has to use its own internal energy to do that, and so its temperature plummets. That's the basic principle behind how your refrigerator works. Okay, so this brings us to a super common misconception. Because people hear adiabatic means no heat transfer, it's really easy to jump to the conclusion that it means no energy can change at all. But that's not the whole picture. And this is the absolute key distinction. Adiabatic means no heat crosses the boundary. Q equals 0. It does not mean the total internal energy is stuck. You can still change it, and sometimes you can change it a lot by doing work.
You're just using a different door, so to speak, to get the energy in or out.
But why? I mean, why does heat always flow from hot to cold? Why does the universe seem to have this built-in obsession with reaching equilibrium? The answer to that takes us to one of the deepest, most fundamental concepts in all of science, entropy.
You know, the easiest way to think about entropy is just as a measure of probability. When you let energy move around freely, like through a diathermal wall, it's naturally going to spread out into whatever arrangement is the most statistically likely. And it just so happens that the state with the most possible ways to arrange that energy is the one where the temperature is the same everywhere. So equilibrium isn't some weird magical force, it's just the universe betting on the most probable outcome.
And look, these ideas are not just abstract things for a textbook. They are the invisible architects of our entire technological world, and they shape everything from what happens on a lab bench all the way up to the fabric of space-time itself.
Seriously, the principles of these walls are everywhere. They are critical for super precise instruments, for huge industrial processes, even for life itself. Your own cell membranes are playing this game. Aerospace engineers are in a constant battle with thermodynamics, trying to build more and more effective adiabatic walls to protect satellites. In fact, the entire mathematical framework we have for statistical mechanics is built on this one fundamental distinction.
So far, equilibrium seems pretty simple, right? Everything just ends up at the same temperature. But what if I told you that's not always true? The universe is way more clever than that. What if the nature of the wall itself could fundamentally rewrite the definition of what equilibrium even is?
Get this. In some really bizarre quantum systems, you can have a boundary that's like a picky customs agent. It only lets a high-energy photon cross if a low-energy one is swapped for it. And in that weird scenario, the system reaches equilibrium when the side giving up the high-energy photons is actually hotter than the side getting them. Just think about that for a second. The wall itself has completely rewritten the rules of the game. And this even happens on a cosmic scale. It's called the Tolman-Ehrenfest effect. It says that for a tall column of gas sitting in a gravitational field to be in true thermal equilibrium, the bottom actually has to be hotter than the top. Why? Because gravity itself is acting like a kind of boundary. A particle of light loses energy as it fights its way up against gravity, so it has to start out hotter at the bottom to make it. The boundary of space-time itself is changing the rules. So this is the single most important thing to take away from all of this. The wall is never just a passive box. It is an active gatekeeper that dictates the rules of engagement for energy. It doesn't matter if it's a simple piece of aluminum, a weird quantum filter, or the curvature of space-time itself. The boundary defines the physics. And this really leaves us with a final, pretty mind-blowing thought. If the simple act of drawing a line and defining its properties can lead to totally different physical realities, it really makes you wonder, what other fundamental rules that we take for granted are really just a consequence of the boundaries that we've happened to draw so far?